In NCEA Level 3, we are only going to be looking at one type of exponential, and that is an exponential in the form function of x equals e to the power of x. Now, the function e to the power of x was designed to differentiate to itself. So the derivative is also e to the power of x, and that is by definition. And so we are going to use that rule to allow us to differentiate harder exponentials. We are not going to look at functions in the form 2 to the power of x or anything other than e in level 3. Of course, you're not going to get just e to the power of x. It's going to be a little bit harder than that, but we're going to use the same rules that we've learnt previously to help us with this. We are going to differentiate this by doing dy dx. We're going to start by rewriting the function because that's the definition of above. So 3e to the power of 2x. Now we haven't done anything with the 2x yet. So really it's just a use of the chain rule again. We're going to multiply by the derivative of that power times by 2 to get 6e to the power of 2x. And that's it. It may look more complicated and you're going to have to use your laws of indices to make questions simpler. So for this question, we can split this up to e to the power of 2x over e to the power of x minus e to the power of negative x over e to the power of x. That gives us, subtracting our indices because we're dividing with the same base, so e to the power of x minus e to the power of negative 2x, which we can differentiate. E to the power of x differentiates to e to the power of x, and this one we're going to rewrite it exactly as before, and then times by the derivative of the power, times by negative 2. That gets us to e to the power of x plus 2e to the power of 2x, negative 2x. Number 3, powers of powers. We could rewrite this as y equals e to the power of 2x plus 8. Powers of powers says you multiply the powers together. Differentiating dy dx. Rewrite the e and times by the derivative of the power times by 2. Final answer 2e to the power of 2x plus 8. And finally, rewrite the e to the power of x squared, and times by the derivative of the power times by 2x to get 2x e to the power of x squared. Now you may be wondering, what is e? E is a number, just like pi, and e is defined as the limit as x approaches infinity of the function 1 plus 1 over x to the power x. Now, in our calculators, we can't actually use infinity because it's not a defined number, but we can use a number like 1,000,000 to pretend. Now, if you go too much bigger than 1,000,000, the calculator treats 1 over 1,000,000 as 0 because it can't handle it. So let's just use 1,000,000 and substitute 1,000,000 into this formula. So 1 plus 1 over 1,000,000 all to the power of 1,000,000. You get 2.718, and it goes on forever. This won't be the exact value of e, but in your calculator you can also do e to the power of 1, which is 2.718. So it's close enough. So, now that we know what the value of e is, what is e to the power of x? Well, there was this person called Leonard Euler. He noticed that when you differentiate polynomials, that you always get a different function. He wanted a polynomial that when you differentiated it, it would be the same function. So he defined this polynomial as y equals a plus bx plus cx squared plus d x to the power 3 plus e x to the power 4 plus f x to the power 5, and it just keeps repeating forever. Doesn't stop at z, it just keeps going to different letters. When you differentiate this function, it should give the same as the previous one. So we differentiate it. A differentiates to 0, bx differentiates to b, cx squared differentiates to 2cx, dx cubed differentiates to 3dx squared, and we keep going. 4e x to the power 3, 5f x to the power 4, and so on. But if this polynomial differentiates to the same, then surely the derivative will also differentiate to the same. So we're going to just keep differentiating this polynomial until I get f as the constant, but in theory it would go on forever. So y dash dash is 2c plus 6dx plus 12ex squared plus 20f x to the power 3. Third derivative is 6d plus 24ex plus 60f x squared. The fourth derivative, I'm just doing y4, is 24e plus 120 fx, and our fifth one, now this is not y to the power 5, it's just y to the fifth derivative, is 120f. Now if these polynomials are all identical, that means that in each of these columns these numbers should be the same. So we're just going to look at the first column. This says that a should be equal to b, which should be equal to 2c, which is equal to 6d, equal to 24e, equal to 120f. So we started by going, well, what's the easiest number for a? Let's just make a 1. That means that b must also be equal to 1. That 2c must also be equal to 1, so c will be a half. That 6d is equal to 1, so d is a sixth. That 24e is equal to 1, so e is 1/24th. And that 120f must be equal to 1. F is 1/120th. Of course, this will keep going. Now, it doesn't necessarily look like a pattern right away, but there is actually a pattern going on. B could be written as 1/1, and so could A. Now, there's not that much interesting going on in A and B, or C, but D, 6 can be written as 3 times 2 times 1. And so we can see that C could be written as 1/2 times 1. And B is just 1/1. E could be written as, or 24 is actually 4 times 3 times 2 times 1. And 120 is 5 times 4 times 3 times 2 times 1. Now what's going on here is something called a factorial. A factorial is a repeated multiplication starting with a value and then going down 1 each time until you get to 1. And so that's sort of implying, well, that C is equal to 1/2 factorial, D is equal to 1/3 factorial, E is equal to 1/4 factorial, F is equal to 1/5 factorial. If you were to keep this pattern going down, we'd expect B to be 1/1 factorial, I would actually expect a to be 1 over 0 factorial. 0 factorial is a bit of an abstract idea because, well, when all the other ones you started at the number and you went down to 1, but at 0 you're already starting at 0. A factorial tells you how many ways a different set can be written. For example, if you had two numbers, 1 and 2, you could write that as 1 and 2 or 2 and 1. So this is equivalent to 2 factorial, because there are two numbers. It can be written one way, two ways. So 2 factorial is 2. If you had a set with just one number, just 1, that could only be written in one way. So this is equivalent to 1 factorial. It's only one way to do it. So 0 factorial is how many ways can you write a set of 0 numbers? Well, actually, here's my set. It's got nothing in it. That can be done one way, so 0 factorial is actually equal to 1. With this repeating pattern, we'd then expect the next value to be 6 factorial, then 7 factorial, etc., etc., etc. Putting this all together, we then get our polynomial is y equals just the 1. B is x, so that's x, plus x squared over 2 factorial, plus x to the power 3 over 3 factorial, plus x to the power 4 over 4 factorial, plus x to the power 5 over 5 factorial, and this will just keep going on forever until you get to x to the power n over n factorial. Now this is actually a polynomial that is equivalent to e. So Euler called this e to the power x. And if you were to try different values of x, so x equals 1, and substitute this into this formula, but don't stop at x to the power 5, stop at maybe x to the power 10, you'll get a value very, very close to e to the power 1. If you sub a value of x equals 2, you'll get a number very close to e to the power 2. And so, because he defined e to the power of x to be this polynomial here, that means that by definition, the first derivative of e to the power of x is also e to the power of x, simply because that's the way it was built.